Hello YouTube and welcome to this channel. In this tutorial I'm going to start a new chapter which is going to talk about the transient simulations within the Maxwell simulator, Ansys or Ansys, whatever you want to call it. I'm going to start with the very simple simulations, and that's I'm going to use one of the examples that I've created like in the tutorial number 210 about the reluctance motors. So what you want to do is if you haven't seen that, you want to go back to chapter 2 and look up for the tutorial number 210, and over there you can see in the part 1 how you can create this motor and how you can set up the coils and excitations for that. And over there I was using magnetostatic, and over here I'm going to use the same model but using the transient simulations to study the performance of the reluctance motor. Okay, let's assume that you guys already have that file or already created that. So you're looking at a 4-phase reluctance motor, which each phase has 2 coils. So we basically have two coils per phase, and you can see them in a different colors. We have black, red, yellow, and green for different phases. And what I'm going to do is the first thing that I'm going to start is I'm going to go and basically get rid of all these current excitations that I have, since these guys are basically current excitations. And the reason that I'm taking it off is because when you go to the Maxwell 3D and go to the solution type to change it first of all from magnetostatic into the eddy current, into the transient study for the magnetic studies, what will happen is we do still have a current excitations within the transient. And what I'm interested here is not the current excitations, but it's coil terminal excitations. You might ask, what is the coil terminal excitations? Well, what it is the coil terminal excitations will excite a coil, and you can say the coil is a solid coil or it's a stranded coil. You can say the coil is excited with voltage, or you can say the coil is excited with current. One thing that I have to tell you over here is when you have current coil terminals, you can have more than one coil for your windings. So you can have a windings and you can say, okay, this windings has 2 coils. But you have to be very careful about that, because if your coils are supposed in one phase, for example, we have 4 phases here and we have 2 coils per phase. If these 2 coils are in series, it's good, because the winding terminal assume that these coils are in series, and they put them automatically in series. But if these coils are not in series per phase, so you have each phase 2 coils, and these coils are not series, they are in parallel, then you need to have 2 different windings for each coil. And then you can decide that, okay, the phase of the excitations for these windings are the same, so they are in parallel but having the same phase. So remind you one more time that for for basically windings, Maxwell always consider by default that the coils that you add inside the terminal coil excitations, or the coils that you are adding in each windings, are in series. Okay, so that's a very brief introduction about what we are going to do. So yes, I'm going to go to the transient, and yes, in transient we still have current excitations, and you can see automatically just recreate those. So what I'm going to do is I'm going to go and press press Control key and go where the actually you can't do that. Well, I guess you have to delete them one by one. Or actually, if you right click on excitations, you can say delete all. So that's good. So you delete all the current excitation, I'm not interested to those. And you go over the sheets and terminal A through terminal D. So these are basically the terminals that we had for our coils, and as you can see, as I'm selecting those terminals are highlighted. Those are just a cross section of coil that we are going to apply our excitation right now. So what you want to do is you want to go and right click on those and say I want to have an excitations, and the excitation is going to be a coil terminal. Okay, so that's a coil terminal excitation right there, and I'm pressing OK on that. So what do you want to call these core terminals each time? So you can leave a base name for those. So the base name here can be coil terminal, and I think it's a good name. You can call it whatever you want. And how many conductors are in this coil? So this is important because now you can actually decide how many turns your coil has. I'm going to go here and say 150. You can say 200. You can say 300. Whatever you want to say. And that's it. You just press OK on that, and you have your all coil created right away, all in once. You don't need to do it like one by one. All in once, you have all the coils selected. Now, what is important here is to say which coil is going to be excited when and how they are actually interact with each other. As I said, when you put two coils in one windings, they are actually in series, and when you can apply one voltage, basically you're applying one phase, right? So they have both one phase but in series. Let's give you one quick introduction about the windings. So right now I'm going to right click on excitations. You have different ways to do that, of course, but I'm going to just right click on excitations and go say add windings, and let's call that winding number 1, and see what exactly we want to do with that. I'm just trying to make sure that okay, so windings can either be current or voltage. So what's the difference between windings and coil terminal excitations? The coil terminal excitations is a gate for you to apply whatever you want to do. So when you say coil terminal excitation, you are basically defining that here's my gate to start doing the excitation, whether this excitation is going to be current or it's going to be a voltage, whether there are two coils in series or it's just one coil in series. So this is how you basically define. So don't mistake that the coil terminal excitations by itself is not an excitation. As you saw when we are assigning the excitation, we just said how many turns the coil has. That's it. We didn't say anything else. So remember, the coil terminal excitations is just a gate. Now it's just a port. Let's call it, it's just a port for our excitations. Now when I design the windings will close the circuit for us. So consider this picture that I'm actually going to put it here, and you can see that the current excitation actually, let's go with the voltage excitations first. So consider this picture here now, and you can see that the equivalent circuit that you have for the voltage excitation windings. As you can see, you have a voltage source, and then what you have is a line inductor, which is the inductor that is shown here in the inductance part. Okay, and you have an initial current. Well, the initial current actually is just an initial condition that you can give it to the solver. To me, put it 0. If you have some certain applications that you want to actually care about that, put the initial current something that you know it is. But for most of the case, just leave it 0. The resistance basically would be the resistance of the windings and whatever adapters or whatever you have which you know causes some resistance. You can add it up here. This resistance will at the end of the day causes some power dissipations, and therefore will affect your overall efficiency. So if you are studying the efficiency of the motor, here is the place that you can put the resistance. As I said, the resistance of winding is one of the resistance here, so you can actually put some numbers over here. And the inductance here are, as I said, extra inductance that you might not model with the coils, but it's there. So let's say you have a very long wire that is not a coil, but it's a long wire, and that long wire might have some inductance, so you can add it up here. If it's not important and you don't have that much of an inductance, just leave it 0. Okay, and lastly is the voltage. So the voltage that you are applying is is a constant voltage. You can have a function or you can have a piecewise linear curve. Whatever you want to do here is available. Why? Because we are in a transient. In a transient, you can do whatever you want. And so that basically concludes what we have over here. The number of branches here, you put it 1 because you already said we have 150 turns for my coil. So then you don't need to do that. Let me just show you the current excitation. In the current excitation, you have the model like this. And as I said, for the coil A, which we have coil A1 and coil A2, you just put them in series and you don't have anything else to actually manipulate. So you just put the number of current that you want to put and that's it, done. Okay, so this is basically the two different excitations that we have, and we do have an external excitations, which is very funny. So when you go to the external type of the windings, you can have a circuit editor, which I will introduce you later in different tutorials. And I guess I went through that in one tutorial, so it's not, it shouldn't be very not familiar with you. But anyway, so the external type, you can draw your own circuitry, whatever you want to add. You want to put a transformer, you want to put a MOS switch, you want to put a circuit that you got from MATLAB. You know, you can put whatever you want to put there. With your excitation there, you put like a pulse, gate, and then you know, the PWM, whatever you want to put there. And then you basically, what you do is you just drop a winding there with the same name, or you can actually do a trick that you open up the editor, the circuit editor, from this winding, and you basically have the windings that is associated with this coil or this Maxwell file right into the circuit editor, and basically you can put whatever you want to do, and you are not anymore constrained into this series or current or voltage type of excitations. You can have whatever you want to do, and that would be the external type. And as you can see in the external type, the only thing you can talk about is the initial current that is in your coil. That's it, nothing else. And everything else is done outside, and you can do it totally customized. I will give you a tutorial on that as well. But let's go with the voltage type and basically start our simulations right there. So the voltage type, we have a lot of options. Number one, I'm gonna have a stranded coil. I did say that the coil has 150 turns, so definitely it's a stranded coil. So make sure that you tick there. And the initial current can be 0. The resistance for the coil can be very small. In this case, I'm going to put 2 ohm. And then the inductance of the, if I have any other inductances, no, I don't. And the voltage that you want to apply, it can be 120 volt. You can apply sine wave, or you want to have whatever you want to do, but right now let's say that we apply 120 volt in the peak and see what are the forces and everything that you want to study at that time, and you can press OK on that. And now we have our first windings. Okay, now what you want to do is you can right click on the windings, or you can actually click on this too, I believe, and then you can say select assignment, oh no, add to winding. And basically, so if I select these two, which I can't, you can say add to winding 1, and then number 2 you can say add to winding 1. Also, you can right click on winding and you can say assign coil terminals, and then you can select from the terminals. Okay, now let me do 3 more windings, and this time I'm going to be fast because I'm not going to explain you anything. So same 2 ohm and basically 120, and this is 2 ohm. I hope that I put 2 ohm for the resistance, not the inductance. So let me just double check for my windings. Yeah, 2 ohm for the resistance. And again, here I'm going to do this time with assigned coil terminals. Oh, add terminals, sorry. So you can add terminals, you can say this and this, 3 and 4. I just press the control key and then press OK. Oh, you can do it one by one. What? To assign a coil terminals to a solid windings. Oh, Sorry. So the mistake here is I forgot to say it's stranded. So it realized that the coil is 150 turns, and the winding says that I am a solid winding, which means that my coils are all solid. So it doesn't make sense for it to add a non-solid coil. So now if I change that to stranded, you can see that 3 and 4, you can easily add them. One last time, I guess. Add. And then I want to go with the voltage and 120 volt and OK, and again add terminals, this one and this one, OK, and lastly to 120 and press OK for that, and of course add terminals. Let's do this. Okay, what? Oh, okay, again I forgot to put the stranded, so right there. And let's do this. Let's do the last part, and there we go. So now we have all our excitations all connected to the windings, and that's basically it. This is how you excite your ports. Now, one other important things that you have to take care of is how accurate your simulation is. The accuracy of your simulation is related directly to the accuracy of your meshing. And now to help the simulator to do a right meshing, you have to give some clue to the simulators that which parts requires finer meshing. Of course, the simulator is smart enough to find the mesh each time that the resolution is not achieved, but you know, it's better to give it some clue so it do it faster. And one thing I can do right now is I press Control and A and select everything, and over there you can basically change the transparency of everything to some other like lower like than 85%. So I'm gonna put it like 50% and press OK. So now you can see the coils and everything better, I guess. And anyway, so now what I'm going to do is I'm going to go and select the coils. You can select each coil by selecting them and then press Control key and then go over the selections, or you can just select them from here. So these are the coils that we have, and I'm going to go and select all of them, and I'm going to right click on that and say, you know, I want to assign a mesh operation, and this time I'm going to make sure that inside these coils I want to have so let's call it the coil mesh, just to make sure that the names are like make sense. Okay, so the coil mesh, I want to make sure that the number of the total tetrahedral elements inside this selection, which is if you look at it, it's 8 different coils, are no more than 16,000. What that means is each coils roughly will get 2,000 tetrahedrals inside that. Okay, so that is a good clue for the meshing engine to understand that we are okay if you go over all the way to 16,000, and we actually like to do that. So it will try to go through that fine meshing. Also, let's do the rotor and the stator, and I'm selecting both of them and go to the meshing, and same thing here. I'm gonna say mesh rest, meaning that the rest of the circuit, I mean the design, and over there I want to say perhaps 4,000, which is again 2,000 tetrahedral per rotor and stator. Okay, let's press OK for that. And lastly, you need to assign an analysis. The analysis that we have here, you can say, okay, we have a start time and a stop time. The stop time can be 20 millisecond, for example. This is 20 second, and you can select 20 millisecond. And the accuracy, you can leave it to be 2 milliseconds. You can make it 1 millisecond, but it's basically take a lot of time to finish, so you can do that. Let me just tell you one other 4 things here that are important. One is when you go to the save field, you can say that I want to have the fields at this time step. So select your time step, or you can either say single. You can basically or you cannot say it's single. So okay, so you have to, no, you can't say add single point. So you basically can add whatever single point that you want to say and then add them, or you can say linearly from 0 to 10 milliseconds I want to have every 5 milliseconds you save that, so you can actually get a at the end of the day you can have an animation of how the coil, how the basically what do you call it, the fields are actually moving, which is pretty awesome if you want to do that. In the advance, also when you are doing some using the calculator, if you don't save that, the only fields that you have is the last pass, the last I think the last stop point at the time, those fields, so you cannot have access to any other fields. So that's a good point to actually save them, but saving them will cause a lot of data storage, so you will have a lot of data storage at the end of the day. So if you don't have that much of a room for that, you don't need to do that. In the advanced mode, you can import mesh, or you can actually import the non-linearity, meaning that you already done some simulations, you demagnetized some of the part of your motor, and now you want to use the demagnetized motor and start from that point. So in that case, you don't use the nonlinear BH curve, but you use the dynamic magnetization data that is already linked to the other basically model, and you can use that. And the rest is not that much important, so I'm going to go over that and finish those. And yes, you do this and you get an error for the excitations and the eddy current effect. Well, one thing you can do is you can go and to the Maxwell and to the excitations, and to basically here set eddy current effect, and you can see that the eddy current effect for all of these guys are not there. And the reason is because we already said that the coils are stranded and had like 150 turns, and honestly the eddy current effect is not going to change that much of an impact on the skin. Basically eddy current cause a skin effect, so we don't have that much of a skin effect, so we don't care about the coils that much. And when it comes to the rotor and stator, you can say, you know what, I kind of want to see what will happen if I have eddy current effect set for the stator and rotor, and then you can basically see what will happen later. But it's not recommended. You can just leave that warning unattended. But if you do that, if you select one eddy current at the end of the day, you will see that everything is passed and there is no warning there. So I'm gonna run the simulations and come back to you with the results and showing you the results of that.